All right, today's goal is solving exponential equation. Example number 1, solving by equating exponents. So here we have a base raised to an exponent and another base raised to an exponential expression. So the goal here is to get the 9 to match this 81, or the 81 to match the 9. And then if the bases match, of course, it means the exponents have to also match. So I'm not going to change the 9 because I know I can change 81 to 9 squared. And so I'm going to leave this 9 alone. So this is going to be 9 to the 2x still. But I can break 81 down, and we're not going to break it all the way down, as a matter of fact. We're just going to change it to 9 squared. All right? And when you do these problems, you want to think ahead a little bit and say, look, I know that I can make 81 into 9 squared, and then I don't have to deal with the 9 over here at all. And then 81 is 9 squared, but that's still all raised to the 3x minus 2. All right, now, before I go on in this problem, there's actually another way to do it. I could make the 9 into 3 squared and the 81 into 3 to the 4th. There's other ways to do these problems, but I try to do them in the simplest, shortest way possible. So sometimes you can change both bases. Sometimes you only have to change one of them. All right, so let's continue. Now, this base matches this base, which means the exponent here has to match all of this exponent, all right, which should totally make sense for those to be equal. Now I'm going to go to one step further with the 9s. I'm going to leave this 9 to the 2x equals, I'm going to multiply this 2 times the 3x and times the negative 2. And so you're distributing that. And so it's really 9 to the 6x minus 4. So we're using laws of exponents again that says if you have a power raised to a power, you multiply. And again, this 2 to the, or not 2 to the x, but 2 times x, sorry. And this 6x minus 4 have to be equal because the 9 and the 9 are equal. All right, so let's finish this up. So I can say then that 2x must equal 6x minus 4. And that's what's meant by equating the exponents. So we'll subtract the 6x. 2x minus 6x is negative 4x equals negative 4. We'll divide by the negative 4. And so finally x is 1. And that problem's done. All right, example 2. Solve by taking a logarithm of each side. Now the directions have changed, and so the nature of the problem did also. I have a 5 raised to the x here. Plus 3 equals 21. Now, I don't have another base raised to an x. And so I'm going to get this 5 to the x by itself. So subtract 3. Right away I get 5 to the x equals 18. And now, if I try to do this the same way I just did the problem previous to this, I'm going to try to get this 18 and make it 5 raised to the something. Well, 5 squared is 25, but there's no way I'm going to get 18 down to a base 5 raised to some number. All right, so I'm going to have to use logs here. Now, what I'm going to do is the same sort of algebra we've been doing before. If I do something to one side of the equation, I have to do it to the other side of the equation. So I'm going to take log of both sides. Now, when I do this, what determines the base of my log is the base of whatever you're trying to solve that has the x as the exponent. All right, and so that 5 right there that I just highlighted is this 5. Whoops, is this 5 right here. It's the base of the log. All right, then I'm going to write this whole inside right inside the log. So 5 to the x. So let me highlight the 5s, that this 5 and this 5. The reason why I chose log base 5 is because of this 5 right here. So I took the log base 5 of 5 to the x. So log base 5 of this side. And that has to equal log base 5 of the other side. Now, the reason why I do this is because properties of logs that we've learned so far, these cancel each other. And so this just becomes x equals log base 5 of 18. This step right here, again, is very, very important. It's very similar to back when we would solve something like x to the fifth and take the fifth root. Those fives match. So we take the same base to match that base to get x to come out, and the log cancels the 5. The log base 5 cancels the base 5. All right, now, this is done if we want to leave this exact. If it says in your directions to round to a certain amount of decimals, then we'll use our calculator real quick. And I'll show the work over here on the calculator. You're going to do the change of base rule, which just says, now I can use log or natural log. I'm going to use log again. I'm just going to take the log of the 18 and divide it by the log of the 5. And when you do this, I really think this is the easiest way to do it, even though other operating systems and calculator allow you to do this a different way. I would always do it this way. So the key to this when you do this is to make sure this parentheses right there is closed. All right? So let's see how this goes in the calculator. Log button's right here. So I'm going to take the log of 18. It's super easy. Now that's the parentheses right there you must close, divided by log of 5. And again, this is a change of base property. I'm going to go ahead and close that one, although it's not as important. And I get my decimal, which would round to 1.80. So this is 1.80. This would be the answer if you were rounding. So I'm going to write this as rounded. Now, if the directions really don't say, you could leave it in either form, which means I would stop here in exact form because it's a lot less work. All right, problem B. Again, you notice that we have a base raised to an exponent, but only one base. And so I'm going to subtract 8 from both sides. So again, I got to isolate this 10 to the 5x plus 4. So let's get this 8 subtracted from both sides. Just like every equation, we want to isolate this with the x on it by itself. So 5x plus 4. So 35 minus 8 is 27. All right, now, just like the previous couple of problems, we want to see if we can get the 10 and the 27 somehow to match, but there's no way. All right, 27 is 3 cubed, but 10 doesn't break down to any 3's. All right, so we're going to have to use logs again. Now, we've learned that there's a special log with base 10. So anytime you see something with base 10, think the logarithm, which is automatically base 10. So I'm going to write the next step, take the log of both sides, just like I did in the other problem. But in this case, the log here that I'm going to use is base 10 because this is base 10. Now, generally, I'm going to write this for a second and then erase it. So I'm going to put this little 10 here in another color. And then 10 to the 5x plus 4. And so I'm taking log base 10 of both sides, and normally would just say the log of both sides. All right, and that equals log base 10 of 27. All right, now, once you see this, generally we're not going to write that 10 as the base. So I'm going to erase that little 10. I'm going to try to erase it. Hey, get out of there. Oh, hey, look at that. I'll fix that in a second. All right, so this is still supposed to be log. All right, now, we don't write the little 10s. Just like when we take a square root, we don't put the little 2 in the corner. So this is still a little 10 down here. So this 10 and the log base 10 are going to cancel. So this 5x plus 4 comes all the way out. Very similar to the last problem. So now I have 5x plus 4 equals log of 27. Again, really log base 10 of 27. So now we just have to solve this for x. So I'm going to subtract 4. The answer here is going to look a little strange, but it's fine. I'm going to go up here. So I've got 5x is going to equal log of 27. Now I'm going to write this with parentheses. So I've got log of 27, subtract 4. So this makes sure that it doesn't look like the log has the 4 in it. So it's log of 27, subtract 4. And then the last step is to divide by that 5. And so when I divide this 5 then, and it's the whole thing divided by 5, I will have my final answer. So log of 27 minus 4 all over 5. Now again, that's exact. I'm going to go ahead and show you how to get this in your calculator real quick. Just because it can be a little tricky, so I'd show you how I would do it. Real quick, I would just take log of 27 and then close that parentheses and then subtract the 4. Make sure you close that parentheses. Hit enter and then just real quick divide by 5 at the end. So I would do it like that. And you get, as an approximate, x equals negative 0.51. So exact, approximate. All right, now here we have a problem that looks even a little more different than the previous couple. We have an e here. Now remember, e is a number, but it's special. We keep it as e, but it really stands for like 2.718. All right, we're just going to leave it as e though. And as soon as I see e in a problem like this and I'm logging both sides, I think natural log, because natural log undoes e. So it's just a special log with base e. So again, I'm going to divide this by 40 to get the e to the 0.6x by itself. So divide by 40. All right, when I divide by 40, of course you can use your calculator on this. I'm going to get 6. So e to the 0.6x, careful and don't lose that little decimal. It's hard to see there a little bit, equals 6. Now, I've got this base e by itself, so I'm going to natural log both sides. I know this is a little strange, but natural log is simply a special log with base e. All right, and that equals natural log of 6. Now, just like the last problem where I didn't write the 10, I wrote it and erased it real quick. I'm going to show you there's a little e down here as a base that we don't write. All right, and we don't like to write it there because it's guaranteed that that base is e, just like log with a 10. All right, so I'm going to go ahead and erase that now, but that's really what it looks like. All right, so now this natural log cancels that e because there's a base e here. And so I get 0.6x equals natural log of 6. All right, and the last step, I'm going to go ahead and squeeze in here, is divide by 0.6. And then this is x equals natural log of 6 divided by 0.6. So, I'll circle that. I haven't circled all my answers on here. I really should. But now, if you go ahead and divide that as an approximate, you'll get x equals 2.99. I'm not going to show that in the calculator. Again, if you do that, make sure when you do this, the parentheses are open here, and you got to close that one, the second one. So here's the approximate. All right. So problem D. This one looks really complicated. However, it's very similar to the other ones, just a lot more steps. I need to get to this e to the negative 3x all by itself. All right, whenever the variable is in the denominator, you want to multiply both sides by the entire denominator so it'll cancel. So really what I'm going to do here, and I don't have a lot of room here, I'll show it way over here. I'm multiplying both sides by 1 plus 10 e to the negative 3x. So when I do that on this side, it's hard to write over here, and then I'm going to do the same thing over here. Then this will cancel this, and all I will be left with is this 50 over here, and then 40 times 1 plus 10 e to the negative 3x. All right, now I can divide both sides by 40. I could distribute here, but it's a lot easier to divide by 40. When I divide by 40, the 50 by the 40, I'm going to get 1.25. And now we're running out of time. I'm going to let you finish this from here. It's very similar from here, like the very last problem I just did right before it, part C. So have the answer to this done for class, and we can check it. Okay, we are done.